Hi, my name is David Inouye, and today I'll talk about our work, automated dependence plots. So partial dependence plots have been a widely used tool to understand and validate a model. And as a running example throughout this presentation, we'll talk about automated loan application decisions. And so on a simplified viewpoint, we might think about a loan amount on the x-axis and loan duration on the y-axis. And each point is an application. And we're going to take essentially a slice of the model along a single dimension. So all the other dimensions are going to be held fixed. So in this case, we're kind of varying loan amount, but we're keeping the loan duration fixed at a particular value based on the data. And the target data points are the red data points. So we can show the model along these slices just using a simple line graph, where here the case, the y-axis is the model output and the x-axis is just one particular feature. We can do this for different examples. This is what are known as instance-specific or ICE plots. Now, if we take the average of those over the whole data set, then we get what are known as the partial dependence plots. So this is kind of the average plot over all instances. So the nice thing about these graphs is that it's kind of fairly simple to interpret because it's just a simple line graph. So you're taking possibly a high dimensional model and you're showing kind of one-dimensional slices of it. However, the PDPs naturally suffer from two potential issues. One is a user must manually sort or select interesting plots. So they have to look through and visually look at each of these plots and see if there's any interesting or what they might mean. And for high dimensional data, this is a ton of possible plots. And if you train different models, each model will produce different plots and so forth, and different data points could produce different plots. So there's a lot of possible plots to sort through. And secondly, PDPs generally only show kind of a single dimension, right? Changing one dimension at a time. But there, you might want to think about changing multiple dimensions at a time. And so in our paper, we essentially first formalize what we mean by plot interestingness. And so we kind of very carefully define some utilities with respect to that, depending on the context. And then two, we want to generalize PDPs along sparse linear directions. So we're not just doing axis-aligned directions. And then finally, we demonstrate ADPs on multiple machine learning use cases. So as a first utility, we start with something kind of fairly simple, which is to compare one model or the original model to some alternative model. And here F is the original model and G denotes an alternative model. F tilde and G tilde kind of correspond to a slice of these models along the same part of the input space. L is some standard loss function like a mean squared error. So some examples of this are, if you want to compare a random forest and a DNN. So here you might want to say which kind of slice kind of looks the most different between the random forest and the deep neural network. Allows you to kind of inspect the differences between these. Another one might be a constant model as the alternative. So here you fix the alternative model at the original prediction value. And you're kind of trying to find out a direction maybe that differs a lot from this constant model. Another example might be an alternative model that's just a linear local approximation around a particular point. So that's what we have here on the bottom right. We're kind of approximating the model with a simple linear model. And we're kind of determining how much does our true model differ from this kind of approximation. So this could be interesting, for example, in Lime type explanations. Another class is called the functional property validation utility. And here it's a similar idea. We're comparing two models, F and H, but H is kind of optimized over a set of possible models, H. And these are just actually one-dimensional models. Big H is just a class of 1D functions that have some particular interesting property. And if you discretize this over kind of multiple different kind of a grid of samples, then this can be simplified essentially to a one-dimensional regression problem. So if you care about, for example, if H is the class of linear functions, you can use linear regression to solve this problem. If you care about monotonicity, you can use isotonic regression. And if you care about something like Lipschitz boundedness, you can actually use constrained least squares. Again, these are all 1D regression problems to kind of understand these one-dimensional line plots. So now the second part is kind of directional dependence plots, which generalize beyond this axis-aligned dependence plots, which only kind of allow you to change one feature at a time. So now the slice doesn't have to be aligned with like vertically or horizontally kind of axis aligned, but it can kind of be an arbitrary direction, usually sparse for computational reasons. And then the bounds of this kind of linear direction, so the part of the plot we actually show, we're going to kind of constrain it to be, near the data density. So we're going to use a kind of a simple data density to determine the bounds that we will show. So automated dependence plots kind of pull these two ideas together, the utility and doing different possible directions. And so here's an example of varying both amount and age, kind of linearly changing both of these. And we propose kind of a simple greedy and sparse algorithm to find maybe changing 1, 2, or 3 dimensions. So as an example, suppose in the loan application you think that monotonicity is important and you want to try to select between different models. In particular, let's suppose that you've trained 3 different models. Each of them have roughly the same test accuracy, 62 or 63%. But you want to kind of sanity check or understand a little bit more what's going on in the model. So you might use PDP or ICE to visualize the model. And these, look reasonable. The amount goes down for most of these plots. And in this case, we're just sorting by variance, which might be kind of a simple natural thing to sort the plots by, kind of naive way of doing things. But if you really care about monotonicity and you expect that the true phenomena is somehow monotonic, here we can use automated dependence plots to kind of optimize kind of the worst case non-monotonicity. So here we're actually optimizing the monotonic utility. And in particular, we can see that a deep neural network has this kind of weird non-monotonic behavior kind of in the worst case. So this might suggest if you're worried about some weird behavior, maybe you should use random forest or gradient boosted trees if this is kind of one of your primary concerns. As another example, ADPs can help us understand out of sample behavior. So things that we might not see in the training data set, maybe we can understand what's going on using something like semantic image transformations where you decrease saturation, your rotation, or blur. So in this case, we try to optimize which set of transformations kind of keeps the value constant, the prediction value constant. And in this case, we find that essentially the model doesn't seem to look at color. Here, the model appears to recognize a stop sign if it's right side up or upside down, but not if it's rotated 90 degrees, right? So this is actually this non-monotonic behavior that we're actually able to find using our method. All right, thank you for listening.